A star much like our own collapses in on itself and disappears from view, leaving behind a mysterious region of space from which nothing can escape. This is a black hole. But how do they work? First, let's watch this massive star collapse. As it begins to fall inwards, everything is literally falling towards the center. Nothing is moving left or right. The only thing that moves is towards the center. Here we see the star reach the size of our solar system, yet still not even half of its mass. We now begin to see light rays bend around the star because of its intense gravity. And that means something special is about to happen. Here is where the star has shrunk down to just 1/3 of its original radius. Now we start seeing the first signs of a neck forming behind the star. At the very center of the star, the gravity becomes so immense that not even light can escape. At this point, the star has reached just 1% of its former radius, and the surface of the star has disappeared over the horizon of the black hole. We are now close enough to see what happens next. And here we go. The collapsing star forms a thin disk of glowing hot gas and dust around the black hole. This is called the accretion disk. We can also see that the intense gravity of the black hole distorts the space around it, forming a lens which bends and magnifies light. This effect is called gravitational lensing. These features are the key to understanding how black holes work. Let's first focus on the accretion disk. You may think the black hole would be a pretty boring place if all you saw was a dark disk of stuff orbiting around it. But actually, this disk is incredibly fascinating. Let's make it bigger so we can have a closer look. When the star first collapsed, everything fell inwards towards the center. Now we see this disk form. This means that the material must be spinning around. Why? Because angular momentum cannot be destroyed. Remember when you were a kid and you used to spin around really fast and then suddenly stop? Your arms would fly out to the sides. That's because your body wanted to keep spinning. Your angular momentum had to be conserved. It's the same idea here. Only now it's happening on a much grander scale. The thing is, though, there's more than just gas and dust here. There are also millions and billions of stars that were once part of the nebula. These stars are still orbiting around the black hole, and some of them will pass between us and the accretion disk, which will make it appear slightly blotchy. This is something astronomers actually observe in real black holes. They can see these stars orbiting around it. They can also measure the Doppler shift of their light, which allows astronomers to calculate both the speed and the mass of these stars. But wait a second. These stars orbit around the black hole, yet they don't get sucked in by its gravity. How do they stay in orbit? Well, it's because they are orbiting around the center of mass of the system, which lies somewhere within the accretion disk. If they were to get too close to the black hole, though, then the gravitational pull would become too strong, and they'd get pulled in. In order to understand how a black hole works, we need to know how does gravity work. So let's start by looking at the familiar example of Earth's gravity. To keep things simple, let's assume that the Earth is flat. For now, imagine you have a ball attached to the Earth's surface by a string. This represents a star in orbit around a planet. In order to keep the ball in orbit, the string needs to be tight. Otherwise, the ball will fly off into outer space. The tighter you make the string, the faster the ball must move in order to stay in orbit. What happens if the string breaks? The ball falls towards the center of the Earth. What if you were in orbit around the Earth and your spaceship's engine failed? The same thing would happen. You'd plummet towards the ground. Gravity can be thought of as a force that pulls objects towards each other. The more massive the object, the stronger the gravity. Now, if we replace the Earth with a black hole, things get interesting. Let's assume that the string is light. In order to avoid being sucked into the black hole, the light must never cross the surface of the black hole. This surface is called the event horizon. Once any object crosses the event horizon, it can never come back out again. You might think this would mean that as the star approaches the event horizon, the light from the star would get brighter, because all the light from the star is being focused onto a smaller and smaller area. And it does get brighter until it reaches a certain point. Then, incredibly, it begins to get dimmer until it disappears completely. This may seem impossible, but remember that as the star gets closer to the event horizon, the light from the star has to travel through more and more intense gravity. The result is that the light gets increasingly blue shifted. Blue shifting is when light gets compressed and shifted to shorter wavelengths. Eventually, the blue shifting becomes so extreme that the light is no longer visible. Instead, it is squeezed into an infinitely narrow band of wavelengths and becomes a burst of gamma rays. This means that if you watched a star disappear into a black hole, the brightness of the star would increase until it reached the event horizon. Then it would decrease until it became invisible. This also explains why the light appears to be bent by the intense gravity of the black hole. The bending of light is known as gravitational lensing. It's just the reason why you can see multiple images of distant galaxies when you look at a black hole. The light from the galaxy is being magnified and distorted by the gravity of the black hole. This effect can be incredibly powerful, allowing astronomers to detect extremely faint objects that would otherwise be impossible to see. Okay, so we understand how light works around a black hole, but what about matter? Well, that's where things get really interesting. You see, when you throw a ball towards a black hole, it doesn't just fall in, it accelerates. The closer it gets to the black hole, the faster it goes until, bam, it crosses the event horizon and disappears. But it's not just the ball that accelerates. Light also gets dragged along with it. This means that as the ball approaches the event horizon, the light emitted by the ball also gets blue shifted until it disappears from view. It's the same with anything that falls into a black hole. All the light emitted by the object gets blue shifted until it becomes invisible. This is why black holes are black. None of the light that passes close enough to the event horizon can escape. This creates a region of empty space around the black hole, known as the photon sphere. One strange feature of the photon sphere is that it allows for stable orbits of light. Here a beam of light can orbit around the black hole without ever crossing the event horizon. This is because the light is always being pulled back towards the black hole by its gravity, but it never quite crosses the event horizon. Instead, the light bounces off the photon sphere and continues to orbit around the black hole. Some people find this hard to believe, but it's actually been observed. In 2012, astronomers captured an image of a star that appeared to be orbiting around a supermassive black hole. What's crazy is that the star was orbiting around the black hole at nearly the speed of light. This discovery provided strong evidence for the existence of photon spheres around black holes. And that means we have learned how black holes work. But there's still so much more to explore. There are lots of unanswered questions about black holes, such as what happens inside them and how do they affect the fabric of spacetime. But one thing is for sure, they are one of the most fascinating phenomena in the universe. So thanks for watching. If you liked this video, please leave a comment below to tell me what you think. And if you want to see more videos like this, please subscribe.